In this video we're going to be talking about zeros of polynomial functions. And what we mean by a zero is, well, if we input the value, well, c here, we're saying c is a zero of the function f, if when we put in c into the function we get a value of 0. Now this holds, or this kind of corresponds to a couple of related facts, one of which is that if c is a 0, c is an x-intercept. C is an x-intercept if c is a real number. Secondly, x minus c is a factor of the function, right? And we saw that in the last video. If a value is a 0, that means we can write that value as a factor. And then lastly, if if f is of degree n, f has n number of zeros, so real and complex zeros. So whatever degree, that tells us how many zeros there are. Now we need one more strategy in order to be able to find most zeros of polynomial functions, or maybe not most of the time it'll work, but just one step further than what we've already seen. And this is called the rational root theorem. And what it says, if we have a function p of x with integer coefficients, and if p over q is a 0 of the function, then p is a factor of the constant term, and q is a factor of the leading coefficient. In other words, plus or minus p over plus or minus q produces all possible rational roots, or zeros, of the function. Now this kind of a lot of math language here, but hopefully this will become clear when we look at this first example. And that first example says, to find all zeros of the function f of x equals 2x cubed plus 5x squared minus 4x minus 3. Also write this as a product of linear factors. So a couple things to notice before we get going here. First, because this is degree 3, that means there's going to be 3 zeros. Okay, so we're going to find 3 zeros. When we talk about linear factors, what we want is we want to be able to write the function as something of this form: x minus a, x minus b, x minus c. Okay, so because there's 3 zeros, we're going to have 3 linear factors. And by linear factors, we just mean each of the x values are raised to the first power. Okay, we don't have any x squareds in the factorization. All right, now the first strategy we would probably attempt here is to factor this by grouping. Because we have 4 terms, that's usually a good thing to test, because that's an easy thing for us to do. Now we could try to do this by factoring by grouping. On the left side we can factor out x squared, we're left with 2x plus 5. On the right we can factor out maybe negative 1, 4x plus 3. This is not going to factor by grouping because those factors are not the same. So grouping's not going to work. Also, this is not a quadratic, so we cannot factor by, or we can't use the quadratic formula. This isn't going to factor very easily, which is what we just saw. So we need a new strategy, and this is when we use the rational root theorem, or the rational root test. So the rational root test says, if we take plus or minus p over plus or minus q, that's going to give us all the possible rational roots. And the idea is we just want to find one rational root, because if we can find out what one root is for f of x, we can divide by that root using synthetic division, and that will reduce this down to a quadratic. Once we get it to a quadratic, we know what to do. So let's figure out what all the possible rational roots are. Now the p-value is right here, and the q value is the leading coefficient. So what this is saying is, find all the possible factors of p. Well, the factors of p are going to be plus or minus 1, and then plus or minus 3. And then the factors of q, well, that's just plus or minus 1, plus or minus 2. And what we want to do is we want to figure out what are all the possible combinations of these numerators and denominators. Well, I could have 1 over 1, so I could have positive 1 or negative 1. I could have 1/2, so plus or minus 1/2. And then I could have 3 over 1, so plus or minus 3, and then 3 over 2, plus or minus 3/2. Now this is saying this list is all the possible rational roots for the function. Now this does not tell us what any irrational roots are. This test does not tell us that. This test does not tell us what any imaginary roots are. So this is a limited test, but it gives us a starting point for what values to test in to see if any of these are zeros. So the goal here is let's just find one value that is a 0. And we do that by testing these numbers in using these numbers as the divisor in synthetic division. So I'm just going to pick a value to test. How about positive 3? So 2, 5, -4, -3. Let's see what that gives us. Bring down the 2. 2 times 3 is 6. 5 plus 6 is 11. 11 times 3 is 33. That's 29. 29 times 3 is, what, 87. Subtract 3, that's 84. So because we don't have a 0 here, what that means is, so this is not 0. What this means is 3 is not a 0 for the function f of x. All right, so we tried 3. 3 is not a 0. So what we need to do is we need to keep going through this process until we find a value that is a 0. So let's test positive 1. My suggestion would be to test all the integers first because those are going to be easier to deal with in the synthetic division. Then you don't have to multiply by fractions or add fractions. So bring down the 2. 2 times 1 is 2. 5 plus 2 is 7. 7 times 1 minus 4 is 3. All right, that's good news. We have a 0. So that's good news. Sometimes you can try a bunch of these values until you find a 0. And we are not guaranteed that one of these is a 0. Okay, this just tells us if there's a rational number that's a 0, it's going to be in this list. All right, so what did we do? Well, we have our function. Because 1 is a 0, that means that x minus 1 is a factor. So I'm going to write this as a factor. And then the 2, the 7, and the 3 makes up the other, or the new polynomial here. So 2x squared plus 7x plus 3. All right, so we found 1 0, and we got this down to one factor. Now, as mentioned, this is quadratic, so because that's quadratic, we know what to do with that quadratic. We can try to factor, or we can use the formula. And this one factors to 2x and x. That's going to be plus 3 plus 1. So x minus 1. So those are the linear factors of this function. So we wrote this as a product of linear factors. And then the zeros are going to be 1, -1/2, -3. So those are the zeros. All right, so we have answered the question. This one's not so bad because all of the zeros, all of these zeros actually showed up in the list when we did the rational root test. This is not typical. So let's look at an example where we have zeros that are not rational. This example says to solve the equation 3x cubed minus 8x squared minus 8x plus 8. And again, this is 4 terms. Let's see if we can factor this by grouping. And doesn't look like it. Actually, I could factor out 8, but that's not going to make a difference. We have x plus 1, or minus 1. Okay, so the point is that those factors are not the same, so cannot factor this by grouping. So what we want to do is we need to use the rational root test to figure out if there's any rational factors or rational zeros. This isn't a function, so we're not finding zeros, but are there any rational solutions to this equation? Okay, so p is the 8. So what are the factors of 8? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Divided by the factors of 3. Well, 3 we could have plus or minus 1, plus or minus 3. So the list of possibilities, we could have plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3, and then plus or minus 8, or plus or minus 8/3. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 16 possibilities. So again, we would need to test all of these until we exhaust this list. The goal here is to find a zero, or to find one solution to this equation. This list is the starting point for that for that journey. All right, so let's just start testing. So 3, -8, -8, and 8. Now, when you're going through this process, so a couple things that can help narrow it down for us. Well, you probably want to test all the integers first, as mentioned. So we would want to test plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay, we'd probably want to do that first, just to avoid the fractions, not because the integers are more likely to be zeros, but because we don't want to deal with fractions if possible. And then other than that, you just kind of have to guess and check your way through. Now, I'm cheating a little. I know what the zero is. The zero is 2/3. I've already gone through this process. I've tested all the integers. None of them work. But I found out that positive 2/3 does work. So let's check that out. Bring down the 3. 3 times 2/3 is 6/3, which is 2. Minus 8 is -6. -6 times 2/3 is -12/3, which is -4. -12 times 2/3 is -8, and 0. Okay, so what we have is a couple ways we can write this. Because 2/3 is a 0, that means x minus 2/3 is a factor. So x minus 2/3, and then 3x squared minus 6x minus 12, that's equal to 0. Now, this right here, x minus 2/3, that's not typically how we would write that, because that means that 2/3 is a solution here. And normally how we would write this as a factor is, well, multiply both sides by 3, and then subtract 2. So 3x minus 2 is the factor. So I'm going to write it that way. You don't have to write it this way. Sometimes a question may say write the factors with only. I guess it may say to write it as integers. I don't know if that's how common that is. So either of these are totally appropriate. Now 3x squared minus 6x minus 12. This one does not factor. This is a problem because we like it when things factor. Now we can factor out greatest common factor of 3. We're left with x squared minus 2x minus 4 here. And again, this does not factor. So what we have to do here is use the quadratic formula. So x squared, well, x is going to equal opposite of b plus or minus square root of b squared minus 4. A is 1, c is -4, all over 2 times a. So x equals 2 plus or minus square root. -4 squared is 4. -4 times -4 is 16. So 4 plus 16 will be 20 divided by 2. And what we're going to get here is x is equal to 2 plus or minus 2 square root 5 over 2. Reduce that to 1 plus or minus root 5 over 1, or just that. Okay, so that tells us that this is two of the x values. So x is going to be 1 plus root 5 or 1 minus root 5. And then that other factor, 3x minus 2, well, we've already seen that 3x equals positive 2x is equal to 2/3. So those are that's one solution, and then we have our other two solutions over here. Writing this out, the solution is going to be x equals 2/3 or 1 plus or minus root 5. That is our solution. Now, this question did not ask us to write this in factored form, but let's go ahead and do that just because working with this irrational number here, it may be less obvious how this factors. So let's see, 3x cubed minus 8x squared minus 8x plus 8 is equal to 0. So if we wanted to write this as linear factors, well, we already know that 3x minus 2 is one of the factors. And then to convert this, x equals 1 plus square root 5, what we're going to do is we're going to subtract 1 and subtract root 5 from both sides. So we'd say x minus 1 minus root 5, that would be a factor. And then the second factor is x equals 1 minus root 5. That's that last 0. We're going to subtract 1 and add 5. So this will be x minus 1 plus square root 5. And then if I just write that 3x minus 2 over here. So this would be the factors of that polynomial. And again, this one doesn't ask us for the factors, but when we have irrational solutions, this is how we could write those as factors. All right, another example says to find the zeros of f of x and write f of x as a product of linear factors. So here's our function. Now, again, this has 5 terms and it's 4th degree, so can't use anything, any of the quadratic strategies here. And because it has 5 terms, we cannot even attempt to factor this by grouping. So the rational root test is really the only thing that we can do here. So this is the p-value, so we're going to say all the factors of -6. So this will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then the q value is just 1. So the only factors of 1 are plus or minus 1 here. And that is 2. All right, so the possibilities that we should test, this is plus or minus p over plus or minus q. So the p-values that we should test are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All right, so again, I've already done this. So I know that 3 is a 0. So 3, we'll divide that into 1, -1, -5, -6. 1 times 3 is 3, 2 times 3 is 6. That didn't work. It's because I didn't write the x term. So the coefficient on the x term is -1, and then we have the -6. Okay, so 1 times 3 is 3. 3 plus -1 is 2. 2 times 3 is 6, 0. So we got a 0 there. So that's good news. And remember, what that means is that x minus 3 is a factor. All right, so the new function is f of x is equal to x minus 3, and that's getting multiplied by, well, remember, we're starting with something that is 4th degree. After the synthetic division, the degree moves down 1 value, so this is going to be 1x cubed plus 2x squared plus x plus 2. Now, I could go through the synthetic division again, but we can check here to see if we can group this second factor, if we can factor by grouping. So x squared, I'm left with x plus 2 plus 1, x plus 2. All right, that's good news. We can factor this by grouping, so x minus 2, oops, that should be a 3 here. I'm just bringing down the x minus 3. So x minus 3 and then x minus 3 here. All right, so finishing up the factoring by grouping, we have x squared plus 1 and x plus 2. That's our function. All right, now it looks like we pretty much have this factored except for that middle factor is not linear yet. So what we need to do is take x squared plus 1 and we need to write this as linear factors. Well, one strategy is to find the zeros of this first, or solve this equation, x squared equals negative 1. Taking the square root of both sides, well, I'm going to get an imaginary number. This will be x equals plus or minus I. And then what we can do is we can take each of these and we can write them as factors. So x minus I is a factor and x plus I is a factor. So writing this function as linear factors, we're going to have x minus 3, x plus 2, and then x minus I, x plus I. So those are the linear factors. And then to write this as 0, or write the zeros here, well, the zeros are going to be positive 3, negative 2, and then plus or minus I. And that gives us our solution. Okay, so the last thing to discuss in this video is called the conjugate pairs theorem. And this is just saying if we have a 0 that is of this form, a plus or minus bi, in other words, if we have a 0 that's a complex number, its conjugate is also a 0. So suppose I had 3 plus 2i as a 0, that would mean 3 minus 2i is also a 0. Similarly, if we have an irrational 0, something like this, 2 minus square root 6, actually let's not use 6 because that looks like it'd be 2 minus square root 7. If that's a 0, that would mean that 2 plus square root 7 is also a 0. So complex zeros and irrational zeros, we say they come in pairs. That's what this is saying. That's what this is saying. And if we look back at that previous example, this 0 down here, plus or minus I, this is fulfilling the conjugate pairs theorem. We would never have a 0 that is just I. We are always going to have the positive and the negative of that 0 if it's a complex 0. And the last example here says to construct a fourth degree polynomial that has 3, negative 2, and 3 plus root 2 as zeros. Now, because these values are zeros, what that means is x is equal to 3, x is equal to negative 2, x is equal to 3 plus square root 2. And to use these values to construct the polynomial, we want to convert these into factors. So this is going to be x minus 3 equal to 0, x plus 2 is equal to 0. Here I'm going to subtract 3 and subtract square root 2, so x minus 3 minus square root 2 is a factor. And then using the conjugate pairs theorem, well, because we have 3 plus square root 2 as a 0, we know that 3 minus square root 2 is also a 0. So writing that as a factor is going to be x minus 3 plus square root 2 is equal to 0. So to create this polynomial, all we do is we multiply all of these factors together. So f of x, our function, is going to be x minus 3, x plus 2, and then x minus 3 minus root 2, x minus 3 plus root 2. Now, I should probably change the directions on this example because the directions just say create a polynomial, fourth degree. I've done that. This is a fourth degree polynomial. But we want to multiply this out. So if we're getting technical about what the definition of a polynomial is, this is not quite there because we need to have all of the terms separated by plus or minus, and we don't have that. So let's multiply this out. When we're doing this, we always want to multiply the conjugates first, because what's going to happen is a lot of the terms, some of the terms will cancel, so multiply conjugates first. So doing so, we're going to have x times x is x squared. X times negative 3 is negative 3x. X times square root of 2 is plus square root 2x. I'm going to write that the other way, x square root 2. And then negative 3 times x, negative 3 times negative 3, negative 3 times square root 2. And then running out of room, negative root 2 times x is negative x square root 2 plus 3 root 2 minus square root 4. And then I could multiply this out, these first two terms together. X squared minus 3x plus 2x will be minus x minus 6. And then many of these terms in this second factor are going to cancel. All of the radicals should cancel. So x root 2, negative x root 2, and then negative 3 root 2, positive 3 root 2. So what we end up with is we get x squared, negative 3x is negative 6x, and then we have positive 9, square root of 4 is 2, so 9 minus 2 is plus 7. Bring down the other factor, and then I'll let you multiply this out. Okay, so when we multiply this out and combine all of our like terms, we get f of x equals x to the 4th minus 7x cubed plus 7x squared plus 29x minus 42.